All right, everybody. Uh, Hi, and welcome to D0034 class, Knowledge Representations and Management. And this week we have two guest lectures. So this is the last week of lectures. And just before I introduce the speaker for today, I want to draw your attention that I published the home assignment that we actually developed together with La Trobe University. So at the end of the class, I will stay online. So if you have any questions, immediate questions, so feel free to ask. You can also ask them in the chat in the meantime. But without any further delay, so let me just introduce Dr. Nishan Mills from La Trobe University. So we have collaboration with this university since many years, and Nishan is the guest lecturer at LTU. And by the way, La Trobe University acronym is also LTU, so we call us LTU Square. So, so, so Nishan is the senior lecturer from LTU South to LTU North. Yeah, and he will introduce the topic of LLMs and knowledge within LLMs, and it is very much related to the topic of your home assignment that you have 1 month on you to complete. So, without any further delay, Nishan, so please.
All right. Hi, everyone. Good to meet you. And as Professor Evgeny said, yes, I am part of LTU Squared, as it were. And there are a lot of
Nishan,
similarities.
is it me who disappeared?
Can you hear me?
Yeah, now, yes.
Oh, sorry about that. Okay, I was just saying, so basically, I'm a part of LTU Squared, as it were, and there are very many similarities between our two universities. Like Professor Evgeny likes to say, I think we're kind of inverses. So we are right down the bottom, you guys are right up the top, and you have a connecting
I
network which
think
is underground.
you disappeared again
Okay.
somehow. And now you're back.
Okay, I'll just keep it like this. Hopefully that's
Okay.
better.
Yeah.
Right. Clearly that introduction is not going well. That's why I keep dropping out. So as I was saying, so I mean the similarities are interesting because we have a overground connection between all our buildings, whereas you have an underground connection between all your buildings. So quite a few connections there to kind of
I'm trying to figure out if it is my loudspeakers, it's my headphones that kind of
Yeah, I
prompt.
I can hear him just fine, so I think it's on your end.
Is it on my end? Oh, I'm sorry
Yeah.
then. Okay,
okay.
sorry. Okay,
Yeah, I
so
hear okay.
yeah, please continue,
Okay,
Nishan.
great. Oh, okay, great. Uh, I think we'll abort the introduction for now. We'll start off with the lecture. Um, So, in terms of what I want to speak about, so this week I thought what we'll do is today we'll just do a coverage of, in terms of theoretically and just from a landscape point of view, a progression towards large language models and where they kind of sit within the knowledge management scape, and also this concept of agents and where that is going, because this year has been kind of dubbed the year of the agent again in more popular circles, I guess. But as you know, the field of artificial intelligence and especially the practical aspects of it are moving on quite fast. And there's nearly a $4 trillion, many trillions of dollars in terms of economy that is being built around AI in itself. And a lot of the focus at the moment is around agents. And if you look at agents in themselves, there's a big dependence on the knowledge that is available for those agents and the representation of that knowledge in a way that the agents can process and also reason on. And so you would have covered a lot of these concepts already in the lectures before. So what I was hoping to do is just give you a bit of a broadscape or a broad brushstroke across all of these different items that are coming up in terms of large language models and agents and the representation of knowledge. And then what we will do tomorrow is essentially look at some of the practical aspects of it by actually implementing some of these or actually looking at toy implementations of some of these concepts in themselves. So as I talk through, if you feel that there's anything that you want to answer, just feel free to raise your hand. We can have a discussion or a quick chat through it as well. So without further ado, I'll just get to my first or introduction. So if you take large language models, I mean, there was a rich tradition that has led up to where we are, and a lot of it has actually come from the concept of language semantics. And that is essentially where it started off in terms of a lot of these implementations, especially around what we consider large language models. And a lot of this, if you had followed this in the previous years, would have been, for instance, libraries like the NLTK from Stanford, where they looking at taking apart language in terms of the semantic construction, and then being able to understand how different concepts actually appeared in those language constructs. So generally the process was you would take up a sentence and you would segment it, you would tokenize it, then you would look at each parts of those speech, almost going from a grammatical point of view, and then doing things such as entity detection and relation detection, and then building that information or that knowledge up from those parts. And so generally what would happen then is you build up a very simple, I will use this term loosely, a knowledge graph, essentially where you're looking at the different entities, and then you're looking at the different relationships between these entities and what the causes and effects have been and how they're actually related to each other. And so all of this was really picked up using just language characteristics, as it were. And so what that meant is that essentially you had to have these libraries or modules that were able to take sentences, deconstruct them into their meanings and tag them. So the parts of speech tagging or the pos tagging as we actually saw it earlier. And then you kind of build up this language tree of these different concepts. And then from this, again, you build up the knowledge that is inside those sentences. And then the sentences actually kind of moved out paragraphs and books. And so eventually you had like a very rich representation of the world, as it were, that was there in the language models. And that is something that you see now as well in terms of our standard. If you look at large language models now, what a lot of people actually talk about is it's a representation of our world or a world model, as it were, just through the concept of language. Now, of course, that has now turned into many different areas now where you actually, obviously, when we look at our world, the way we perceive the world is very different. We perceive it in different modalities. It's not just language, we perceive it through touch, sense, and then you have those other senses as well, everything to do with depth perception, to things like infrared. And so all of this actually come into the large multimodal models that we use now in a lot of senses. But the primary one that was really kind of started off all of this was the language model. So if you have time, it'll be good. Just have a listen to Ilya Sutskever. He was one of the founders at OpenAI. He has a lot of he had a very interesting interview he did some time ago, where he actually looks at large language models and how he draws the parallels between actually being able to use language as a representation of the world in itself. And more recently, if you look at some of the, I think it's called World Labs, they call it World Labs, and they have built out a 3D model of the world, which they actually call a world model. And what they're doing there is you're trying to build spatial intelligence. So that also is a very interesting way, because I mean you can see the progression of how these models are really changing over time as well. And so as we're talking about, I mean, here you have language, you pass it, and you have these parts of speech tagging. And then you kind of break down the sentence with constituents, which then it breaks down into formal phrases, which finally then give you the syntactic roles. So all of this was broadly under this concept of natural language processing, right? And so when you had natural language processing, there were very natural offshoots from this, specifically around things like text classification, information retrieval, so search, as it were, things like question and answer, translations, text generation, summarization, and all of this existed long before we had this flexion point of large language models actually coming in. And all of this, again, were mostly from a statistical point of view, understanding, the presence of these words and how they really represented these concepts as well. So if you look at text classification, some of the examples would have been things like sentiment analysis, language detection, fraud and profanity, online abuse detection, and all of these, even semantic detection, things around trends, urgency. So all of this were a form of text analysis. And if you look at sentiment analysis, that is like probably one of the concepts that has got really flogged through. And so it was something that was foremost in a lot of the research papers. I mean, the first thing that people started to look at were, how do we do sentiment analysis, and how in different ways do we now represent sentiments within like a language corpus. Then, of course, we came to this concept of question answering. Here, what we're trying to do is understand in terms of an existing corpus of work, and then understand questions and answers between that corpus. And then really trying to draw parallels between what the question was and what the answer is in that context. Then, of course, we have this concept of text generation, and that is where we have a lot of the large the language models that are working now. In terms of text generation in itself, this was something that was not really possible with the older types of models, or possible in a very primitive manner. And these actually really took off after the introduction of large language models, specifically things like GPT-2 onwards. So GPT-2, I think it was something in the 21s that it actually came out, or 2020, 2021. And at that time, basically, again, it was very loose in the way it kind of was able to generate text, but those capabilities were quite available there. And in terms of even the context and the length of the horizon, those were things that were available. Then, of course, we came to text summarization. Just being able to take large amounts of text and summarize it with holding the meaning with it in itself to smaller chunks of data. So interesting libraries that were being used at this time, other than the NLTK that is from Stanford, was another one was Spacey. And these models are available and they're still used within production contexts, simply because they are much faster and they're very targeted, very narrow in terms of the way that they are able to do things. So if you don't want really kind of expend a whole lot of tokens, or have a very predicted meaning or a predicted outcome to what you want, and some of these models that are being used, or some of these libraries, these are things that are generally being used even in this context as well. So these are some things around NER, which is named entity recognition. Here, what's happening is essentially any sentence kind of pulled apart, and then we were looking at finding entities which existed within the sentences or corpuses of work. NLTK was the one that I was talking about earlier. Again, it was another Python-based programming language, or Python-based library that was used for natural language processing. And again, you would find, remember how we talked about text sentiment analysis within text? These are some of the other libraries that were used. And all of these is available on GitHub or within Hugging Face. I'll come to Hugging Face in a bit. So you can actually download them and you can actually try them out on corpus of text. And this will be interesting because one thing about knowledge is that you want to really extract knowledge from whatever means that you have available. And these libraries actually provide you a lot of avenues to be able to pull through knowledge or sentiments, entities, relationships, and be able to represent these within your knowledge spaces or knowledge graphs, as it were. So that brings me to Hugging Face. This is a very interesting company that is around. But has anyone heard of Hugging Face or used Hugging Face in any way or form? Just so that I don't keep talking the whole time through. Just open up the chat. Okay, great. And okay. So we have a mixed bag there. So Hugging Face essentially is you might have heard of GitHub, right? So GitHub essentially is almost a world repository for all different types of software projects, as it were. So Hugging Face essentially tries to position itself as the GitHub for models, especially in the artificial intelligence space. So interestingly, it was initially touted as a chatbot, and it was supposed to be a chatbot for teenagers. Again, I mean, the ethical facts of actually having chatbots for teenagers and being able to really market it as such are dubious. But this was something that these two founders were trying to do. They were trying to build this kind of digital friend that you can text back and forth with. And what happened though was the chatbot really didn't take off. What happened is they built this a set of libraries that we were working with in order to create this chatbot, and they were publishing it quite readily in an open source manner. And so what happened was those libraries really took off in popularity. And what happened was a lot of people started to download them from their spaces. And then what happened was because of that, there was a lot of interest in how Hugging Face as a company was really working. And they had some really big investors. So one was Kevin Durant from the NBA. I believe he has moved a couple of he was used to be with the Golden State Warriors, but now I think he's with Clippers. But again, a very influential, what I would say, entrepreneur in terms of investments. So all these people actually really invested in Hugging Face, and from that branch, what they realized is, okay, there is a market or a segment where we can really market all of these different types of libraries for artificial intelligence, natural language processing types of things. And so they branched out and they started to become this repository for different types of models. So even now, if you were to kind of go into Hugging Face, you can create a free account and you can really explore a lot of the models that are being released. So this includes a lot of the major AI model labs or AI models from the major frontier labs as well. Most of them actually appear upon Hugging Face to begin with. So it's a good idea to just kind of open it up, create an account for yourself, and then you'll be able to kind of try out these different models. And most of them actually work within even a Google Colab kind of environment. The code to actually use them is also available. So that's something I would really encourage you to do when you're able to, because these then actually make up those text processing pipelines, which you can then pull the information from in terms of language corpuses. Right. So interestingly, again, what the Hugging Face did was, given their popularity, they bought over a smaller company called Gradio. Gradio, what it allowed them to do was now they were able to build out, if you have a model, now you can actually build out an interface where you can go in and you can try out that model. So what I might actually do is I'll just bring up Hugging Face so I can just show you uh, what it looks like. Right, just give me a second while I this. So it's Hugging Face to CEO. You can log in. And then if you come in here, you have a whole set
Nishan,
of,
are you showing something? Because we still see a slide.
oh, sorry about that. Can you see?
Yes. Uh-huh.
Okay, great. So this Hugging Face, essentially, if you come in here, you have a whole set of models that you can go and explore. And you can see here, there are quite a lot of large companies that are publishing models. So Mistral AI is one company from France. You got Microsoft in there. Um, Also, you have datasets. Anthropic has actually put the interviewer dataset. So this is a really good dataset for you to try out. This is all about Anthropic actually going and interviewing, I think, about 1,250 professionals about how AI is affecting their work. And that all that information is actually in here. So it's like a really good data set if you want to build out knowledge corpuses from. Similarly, there are different types of data sets that are available and different types of models. And what you can do is, maybe I'll go here, you can actually pull up any of these models. Let me just take this model, for instance. And then there's an information on top in terms of what the model is, what are the use cases you can use it for. And also, interestingly, there is also code that you can run to be able to use the model. Let me see if I can, this has changed a little bit from when I used it last. So these are all kind of open models or open CLI tools that you can use to install the model. There's also something called the transformers library, which then allows you to open this out in Python. Let me see if I can find that. Maybe I'll move into a different model. Just look at text generation models. And maybe we can look at DeepSeek. So you can see here the code is available. This can be used within Google Colab in itself. You can pull this code in and you can test it out in any way you want. Also, remember I talked about Gradio. What Gradio essentially did was they gave this thing of spaces where you can actually run models within this space itself. So there is actually embedded here and the models are running the background with a server at the back end. You can actually type in, you can try out the models within this space itself. So, I mean, there's a lot here. And so this is something I would really encourage you to go and check out. This spaces here is basically each of these models actually demonstrated in some way or form. And what you will notice is it's not just text generation models. You have a whole load of models now, including image generation, speech synthesis, 3D modeling, object detection. And so all of these different types of models, you can see all of these are kind of state of the art, which are becoming available. All of them really first land in Hugging Face in itself. So there's something that I would just encourage you to just have a look through. It's not particularly what you might not use within this course, but I think it's very useful, especially if you're looking into knowledge management in itself. This allows you a lot of different models you can use to really extract and model that knowledge from language or even other types of modalities. Great.
I just want to compliment. I think the important thing what Nishan mentioned is accessibility via Python. So you have API to actually hook into different parts of the model and work with internal. So that's really powerful and cool before all.
Yes. So even LNAI, this is another institute you can probably look at. They are open source. They are actually open source, unlike some other open models that model open companies that we have. This is another company to look at. Again, you can see the code is there, all available. Great. What I'll do is let me just jump back to my slides. Again, if you feel you have any questions, please feel free to kind of reach out, right? Great. So that really brings us to the kind of the inflection point of where we move from large language or basically these statistical kind of models into what we know as large language models, right? So all of you might be very familiar with this type of architecture. Essentially with artificial neural networks, what we were trying to do was model some element of the way that our brain functions in the way. And then there was the Hebb's law that came in, which talked about how neurons that are bound together fire together. And so that then created this concept of being able to model, to be able to create the neural networks that form the basis of a lot of the large language models that we use now. From there, we had these little neural networks that started to form. Essentially, what was happening here is you were having different layers. You're having inputs, outputs, layers in the middle, which modeled the weights, and then activation functions, which actually made sure that depending on the inputs, there were certain outputs that were activated and led through, which then gave way to being able to model in some way or form very complex data and very complex information, right? And from that came this concept of word embeddings, right? And so now you can have this thing of inputs coming in and being able to translate themselves. So with word embeddings, what happened was we were able to kind of take words in themselves and then represent them as vectors, which were then available to machines to be able to correspond with or work with. And the interesting thing about these vectors or in terms of these embeddings was there were semantic kind of capabilities or semantic areas that became available. So for instance, if you were to kind of take these kind of words and use these word embedding models to translate them into vectors, you would find that there were similarities in terms of their distance and in terms of the directions that they were. So you looked at man and woman, king and queen, they had a very similar kind of direction. Whereas you could see that here animals were clustering together, where houses were the further away. So there was some semantic kind of representation actually forming when we were actually taking these models or taking these words and pushing them through these word embeddings. So these were types of the semantics that we were seeing through these word embeddings. And so obviously this was quite useful. And so it took on a life of its own. And so you have these multiple models and types of embeddings that really came from that, everything from frequency-based embeddings to prediction or word-based embeddings, and then even to contextualize word embeddings. So, how does a word live within a context of other words or live within a context of a sentence? And how do we create these word embeddings? It's very simple. Actually, you can go into Hugging Face and look for a text embedding model. And essentially, you would take text and pass it through that model. And then you would have several levers that you can pull in terms of the parameters. But those texts passes through the model, and then you get vectors at the other end, which you can now use within a lot of computational tasks. And so this is something, again, that you can try out. So if you take embedding models, you have the Hugging Face models that you can use, quite a few of them available, or you can even use some of the Frontier Lab models as well. So for instance, OpenAI has their own embedding models. Very recently, I think Google came up with their own models, which was a very small model. It can be actually run even within your browser. I think it was just 270 million parameters. So you can really try these out, be able to create your, let's say you can take maybe a corpus of text. Maybe it might be like a book, for instance, Hound of the Baskervilles. You have like readily available text for this. You just take it, you can push it through these models and then see how it really represents itself in a 3D space, or rather in a dimensional space. So let's say if you were to take models, language, and then you push it through these embedding models, and then you were to do like a special representation of it, you would find that there's clusters of these that actually start to appear. Because like you said, the word embeddings have some semantic meanings in there, which they're carrying through, and that shows up in the way that they're clustered as well. So you can see this is a whole set of books that were actually taken and pushed through. And you can see that how the different types of novels are really clustering themselves, or different types of books are clustering themselves within this space. Then from there, we had this thing of, okay, now we're looking just at singular words, right? But what about sequences? If you take words or sentences, there are sequences of words, right? So they started off with the recurrent neural networks or long short-term memory networks or gated recurrent networks. I think I forgot the actual acronym there. But what happened here was essentially each of these different iteration of these models uh, solved a specific issue that the previous one had. So with the RNNs, the problem that you had is you had this problem of vanishing gradient, or basically you couldn't hold the context for too long. The previous information was getting lost. So the LSTMs actually came in and solved one part of that, but it was extremely slow. Then GRUs actually came in and made that maybe 10 times faster. And then from that point onwards, we moved into our current set of architectures that we use within large language models, which is transformers, right? And one of the first that, one thing that was really used quite what do you call prevalently was the BERT model. So basically, BERT stood for bi-directional encoded representation from transformers. So your original transformer models had two parts to it. One was an encoder and a decoder. And with BERT, essentially, you were using only one encoder. And it was able to actually look at a word in terms of its context. It was able to look at from left to right. Whereas if you look at the original transformers, they were just unidirectional. Right. And so using this, there was a lot of different use cases that came into being, including things like generation in terms of sequencing model, machine translation. So the BERT actually came from Google's research arm. And Google, I think, was using this quite prevalently within a lot of their available what you would call a lot of their products, right? And so you'd have seen that Google Translate was always a cut above a lot of the different variants that were available, and all of them used some form of BERT within their background. Then, of course, we came to what we would call large language models as they are, or the first initial representations of them. It's interesting, actually, if you don't have too much of a knowledge or haven't seen this in action. There are two different websites that are given here. One is this from the Financial Times. This is about 2 or 3 years ago. But they actually made it a very nice infographic in how large language models actually represent data. Let me just see if I can. That's right, gated recurrent unit. Let me just see if I can share this. Right, and so this is from the Financial Times. It is a nice little visualization where it really talks you how exactly these
Are you
models are
showing it?
working.
Are you showing it in the browser?
Yes, I am. Can you see it?
No, we see the slide.
Sorry about that. Let me just try it again. Can you see the browser now?
No.
Uh, just now only, you can see?
Yes,
All
yes.
right, okay. Sorry about that. Few too many screens to work with. So basically, this gives you just so this is a non-technical understanding. So just if you're starting off in terms of exploring this area, this is really nice in the way it kind of really figures out how these words are really picked up in terms of text generation. Um, and so it shows embeddings, it shows how the probability of words are really calculated against each other before coming to which words to use within a generation point, and how they are chosen between different contexts in which they are used. So you can have a look at this in your leisure. So this is one thing that I would suggest. The other one that I generally really like the way it's used is this YouTube video here. This is by a gentleman called Three Brown, One Blue. He generally works, he's a mathematician, but he has a very good way of explaining how things work in very simple terms. And so he talks about the transformer and how attention, this concept of attention, where words have context within sentences, actually works. So that's about an hour-long watch. I think that is another thing that you can really look into when you have time. These two will give you a really nice, a background to what large language models mean from a deeper point of view. There is another set of resources that I had. I'll try and share that later. Google also had uh, recently they had a small short course which is about 20 hours where they actually take you through the building of a large language model and how it really kind of comes together. And then you have Sebastian Rashka. He's another gentleman who actually builds a very comprehensive large language models right from scratch, or a transformer-based model from scratch. That he has a book for that. Again, so depending on where you want to really position yourself in terms of this understanding, these are some of the resources that you can look into. Great. So you had large language models. So and if you looked at these initial versions of these models, they were really primitive. Even though they had these capabilities, they were quite primitive in the kind of information they used to give out. So, for instance, if you worked with GPT or GPT-2, you would immediately kind of note that a lot of the time what you were getting back was garbled nonsense, essentially, right? So where that really changed and where we are at the moment is this concept of reinforcement learning from human feedback. Um, so to and this is where there's a really good paper that I'll show you as well. So this is a very interesting graphic that someone gave, which seems to bring this into focus. So you can see the large language models, the way they are, they're trained with all sorts of data from all across the internet, right? I mean, vast troves of data just pushed through these large architectures in order to be able to capture weights. And then you do some sort of supervised fine-tuning where you actually take very clear pairs of what you want in terms of input and output. So for instance, you might ask a question, this is the answer you want. You actually then train this large corpus of information, or these are the large language models, using this supervised fine tuning, right? And so that made it a little bit better. It still wasn't as good. Then what really made it what we have now, or GPT 3.5, or that generation of models, what really made that shine out is this whole thing of reinforcement learning from human feedback. And this was, again, this whole concept of reinforcement learning, right? So again, that's a totally different branch of AI, but that actually made a big difference in terms of having policies and then using those policies to be able to uh, direct the large language models in a way that they give out intelligible information, which is usable, right? And so that is the birth of GPT 3.5. Right. And so this is that paper I would suggest that you go and look at. This was that one of those initial papers. And in here, they really take us through, especially if you go to the appendix of this paper, this was published by OpenAI actually. They really take us through all the different incarnations of these use cases that are being used within these large language models, especially 3.5, right? And so they give a lot of information around, prompts and what prompts actually brought what kind of outputs. And so this is a paper that I would suggest, if you are able to, do have a read through. And it's quite digestible in its form. So it's not very too heavy. And there are concepts that you can follow on from there later as well. Right. So if you were to consider this indicative progress of large language models, you start off with GPT trained, which is generally unsupervised training. You had GPT-2, which was more supervised fine-tuning, like I showed in that diagram before. GPT-3 was scaled up massively. So basically, this is where there was so much information actually brought in, or different corpus and text actually brought in from different models. And this is where a lot of the web scraping or trolled language data sets actually were used. Right? And this is where like some of the ethical issues also come up, because a lot of information that was used was not really attributed. And there's at the moment, there is no clear way to attribute where this information is coming from, right? I mean, these all just kind of picked up together and mashed through these large networks. There's a lot of work that's happening to be able to probe these information. But again, it's not an exact science, right? So GPT-3 is scaled up massively, and like I think the real technological marvel here was the fact that these models, they were able to really do the architectures and the parallelization of GPUs. So there was a lot that went on in the technological side of things that allowed people to train this large context of data, large troves of data through these architectures, right? And that was essentially what really made the difference. And that is why if you take where we are, the frontier labs still have a distance with research labs, just simply because of the fact that they have so much more processing power, like, to the power maybe 10 in terms of GPU processing power, and power in terms of energy and in terms of infrastructure. And that scale is essentially what gave this power, right? Then with 3.5 and GPT-4, this is where it really started to become very usable. So this is where, like, the current incarnations of ChatGPT actually became available, or even Anthropic's Claude or Gemini or whatever the other models, DeepSeek, all of them actually became available with this thing of reinforcement learning from human feedback. And with 3.5 and 4, what you also saw was essentially, now, if you consider ChatGPT in itself, it is a whole platform, right? And sometimes when we use the model separately, what we might find is the model behaves a bit differently to if you use ChatGPT as a platform. That's because the ChatGPT as a platform has a lot of architecture behind it, right? Everything from caching to the different types of models that they use, to the different ways that they inference those models, or where they host it and how they actually run them. It's very different. So what you normally see in terms of research papers and in what is available out there in an open manner, all of those are just the core research that has gone into this. But actually, there is a whole layer of architecture and technology and platforms that has gone to actually making it behave the way we do in terms of our frontier labs. Right? So that's something that's really good to understand. right? And so again, the structure of it has not drastically changed. It's very much the kind of the same. And that's why there were a lot of these conversations about, have we right here plateaued out with the how much a large language model can do with transformers, right? And those conversations, and this is interesting because we recently were at a event with OpenAI executives, and one clear indication is that GPT-6 is quite a long way away. It's not coming in so much to the point that I don't think they're even trying to look at GPT-6, right? So that is just something to note that okay, this is probably we are plateauing, but having said that, I mean, what we can do with these models, we are still just scratching the surface, and this is where courses like this actually really become very important because how can we really use what we have to really take us that next step forward is very important, right? And so I think that is something to just consider as well. And so because if I go to the next slide, so this is again a little bit of a just a little bit of a brief of how these has changed. Uh, I think with GPT-4 we started having the multimodal kind of models where we had text and vision. And there we had this concept of reasoning. I mean, again, I would use reasoning in quote unquote. It is not the kind of reasoning that we generally will associate with humans, but there is some sense of a reasoning pattern, that paradigm that is actually evolving there, right? GPT-4o, basically you had this omni-model concept where you had text, vision, audio, emotion, different types of model modalities being included and which were able to be called up in terms of the platform. And now we have 5.1 and 5.2. That's something I've not mentioned here. But with 5.1 and 5.2, what you would find is the platform is able to switch between different types of models based on the context. And it happens inherently, right? So essentially, they have trained the models to be able to respond in whatever character, depending on the situation that's required. And that's why if you use something like ChatGPT, you would have a thinking sign coming, and you can always stop it and ask it to give the answer immediately. So basically, it's kind of context switching between some of these different models, right? And so, and they are quite powerful in the way that they kind of are able to look at a lot of the common use cases that are being provided, right, or available. So this is just a little bit of a visual way to consider this. So if you look at GPT-4 in terms of its model estimates, essentially we were looking at text, 13 trillion tokens of text, which is equivalent to about 650 kilometers of library shelves. That's quite a lot of library shelves, right? And that is the architectural marvel of what we have been able to accomplish, right? These foundation models, they're trained on this scale of text, right? Uh, and it's hard to imagine that they were able to build something like this in computationally, right? I mean, it's mind blowing sometimes what they were able to do, right? And so that's the interesting thing, right? I mean, the actual architecture itself is not extreme. I mean, it is smart, but it is not similar to our brain. It's a very different kind of beast. Here, what we've done is we have really brute force this intelligence. Right. And this is where, when you look at things like VSA, hyperdimensional computing, they actually stand differently because there is a very elegance to it, which we can see, which is in kind of natural human ability to reason and think. Right. And so these are the two little paradigms you have. So one which is working very effectively in the world at the moment, the other one which is a lot more promising in terms of the direction, but still not quite there in terms of like practical outcomes, right? And so those are the two little things that you have, right? And so if you look at compute size, essentially you're looking at 7 million years of training on one mid-sized laptop, right? Now, that's the kind of compute power that is actually coming in. And if you look at the actual parameters, when you talk parameters, this you're talking about the number of kind of tweakable uh, elements that are within the neural network. We're talking about 30,000 football size fields of Excel sheets, right? So you can see the scale. So this is all about scale, right? And the way that we have been able to crack this is really, throw a lot of money at it and a lot of compute, a lot of power, and then we are where we are at the moment. But the interesting thing is these foundation models now are birthing newer and more capable models, which are much smaller and which are very narrow towards a concept, right? And so I'll mention this as well. The very interesting thing about this is like you won't need a large language model or the massive large language models to be able to do most tasks. Most tasks, especially when it comes to agents, and when you're talking about using agents, all you want to do is just use a very narrow model, right? You just want a subset of that intelligence, which can be easily distilled from the larger models, and that can be run in a very small, architecture. So, for instance, it could be run on your laptop or your browser, and they would work very capably. They are very narrow in their purpose. And so, if you take a lot of these different types of companies that are out there, and especially large companies, what they do is they take these very large models and they try to distill the kind of intelligence that they need just for their specific use case, right? Because I mean, you don't need everything at the one, and it will just confuse things, right? So that is kind of the nuance to take in terms of practically applying a lot of these large language models and systems. You need to kind of look. I think there was a nice idiom that was used: train deep and train narrow rather than wide, right? Great. And so this is where the cloud computing also really came in to view. I mean, it really provided the capabilities for a lot of these um, infrastructure to be deployed very quickly and parallelized very quickly and to be able to be used very quickly in terms of its provisioning, right? So things like elastic scaling, being able to just scale up the compute only at the time it was needed, to be able to kind of run massive data loads over time with a very robust infrastructure underneath, and also being able to provide things like GPUs and TPUs on demand. So all of this was, part of a cloud, part of the cloud computing paradigm, which actually made this possible, right? And so one was cloud computing, the other one was big data, right? The availability of the data and then the availability of the processing power to be able to crunch this data. And that is what has really given us what technology that we have at the moment, right? Because in bygone days, we can't think of even building these kind of server racks, right? Let's say if you take your normal layman, your researcher, or your student, I mean, there's no way that you can really have a server which would be able to process a lot of this information or even run some of these smaller models, right? So cloud actually makes that possible. Right. And so with this, you have this explosion of LLMs now. There's this leaderboard called LLM Arena. They actually do something like the chess ELO ratings, where they actually look at the matching different models against each other on different benchmark data sets, right? And then we look at, how these benchmarks are really setting up the leaderboards. So the interesting thing here is this, right? We have this conversation of, has AGI been achieved or is AGI reachable? And the interesting thing there is what you can see is the benchmark data sets keep on changing because, I mean, there is no real benchmark or no real line that has been drawn as to say, this is what an AGI means. Well, this is general intelligence. And I guess, I mean, this is a personal opinion is that, I mean, I don't think it really matters, right? I mean, it's not important for us that we should build the next human intelligence, right? What is important is that we should be able to build something that will help us to surpass where we are. So, for instance, if you're taking medicine or space travel, do we have something that we can really give some of these brute force crunching tasks to so that we can do the next level up? And so that is where I guess, like, if you look at the intelligence as we see it now, uh, what we really need to focus on in this concept of knowledge management and being able to deploy this knowledge within the research that we do computationally and autonomously, right? If we can do that, I think we are in a good space to really span very quickly over the next decade or so. And so I guess that is what has become kind of a primary goal now for a lot of these frontier labs as well, right? Great. Evgeny, at what point do you give a break or generally do we kind of power through?
Um, how many slides you have left? I mean,
I have about about 20 to 30 more. But I'll go through them quickly. I won't spend too much time.
Yeah, but I suggest we go without break, and
Okay.
then
Yeah, sounds good.
yeah,
All right.
if you finish early, then you finish early.
Yeah, sounds good. Did anyone have any questions to this point? Nope, all good. Okay, great. It is always interesting teaching on Zoom, right? Because because you're speaking, you're not really clear on like what anyone else is thinking. So I had a heavy dose of this when I was actually teaching during COVID. We had a very large cohort, and generally it was my face available to me, and everyone else was kind of mute and cameras off. So
We
anyway,
are
I'll take it.
we are digesting your information flow, so we are
Yes.
good.
Okay, great. Right. So this was a very interesting use case that came up, right? And this is where we're actually really coming into kind of the knowledge management piece as well. This concept of chat over PDF, right? And this was something that really took off during the lockdown period. So for Melbourne,
Nishan,
just yep.
can you possibly zoom in somehow? Because I mean,
Okay.
the
Sorry.
text is so fine. Mhm.
Okay.
Yeah, like this.
Oh, so So essentially, this whole thing was like, can you actually chat with a PDF document, right? And this is something that really took off during those lockdown days because a lot of people had a lot of time on their hands, right? And so they were really trying out these different models in different ways. So this concept of retrieval augmented generation became a thing at that point, right? So the whole thing here was, okay, remember how we talked about embeddings, word embeddings, and similarity, and being able to computationally represent some of these concepts. Uh, so what people found out was, okay, you can take PDF documents, and what you can do is you can chunk them out, right? You can break them up into little parts, and then you can embed them, right? And once you're embedding them, you can actually create something which you would call a vector store, right? So in this vector store, you have millions and millions of these little chunks of data, which is now semantically embedded in a type of embedding. Okay, and you can computationally you can look at similarities and meanings. So what they did was, now when a question is asked, they took the question, they converted it to an embedding, and then they looked within this vector space of what are the other million in the other million test chunks that are available, what is the closest to this question. And then they took all of that and we put it into a large language model and asked it to answer the question. So the interesting thing here was, because because the similarity attributes, the question was able to pull in different types of text chunks which are most relevant to the question itself. And so then that gave a better answer, or a very interesting, not interesting, but a very accurate or appropriate answer to the question the person was asking, right? So this has had many nuances over the years, right? And so this was not something that was possible before this, right? And so with this, now you had this whole thing of, even legal cases, you could kind of chunk them together and you could almost kind of talk to it, right? So you had some really interesting use cases that came. So I think there was one particular use case where someone actually took all of their diaries from their like 9-year-old or 16-year-old self. They pushed it into a large language model and they were kind of chatting to their past self, as it were. So it was interesting, right? Because again, because it's language and there is some sort of semantics there, it was almost like having a conversation with your 16-year-old self, right? So, I mean, and more, I guess, those were just kind of very novelty kind of use cases. But the other use cases were basically now you could take all of the company's information or knowledge and you could represent it in things like a vector store, right? And then be able to pull that up and then be able to chat with that information. And so this architecture, then what it did was it became a bit more nuanced, right? So from a vector store, what they thought was, okay, you know what, let's take it another layer. And using that vector, let's say if you have a chunk that is similar, let's not take only the chunk, let's take that chunk and all the chunks within that same document. Then they started to do let's take that chunk and everything that is very close by to the chunk as well. right? And so while they were doing all these different types of processing techniques, they found that their answers and also what they were receiving became a lot more accurate, and also it became a lot more pertinent to the questions they were asking, right? And so that is this whole concept of chat over PDF, right? So this is one of the core things there. This whole thing of chunking, right? Essentially, you would take maybe a Wikipedia article, and then what you're doing is you're actually breaking it up into different sentence pieces, which are able to then be embedded separately. Remember how we use embedding models? You would take this and you would embed these into a vector space. Now, this chunking also, it varies in the way that it works, right? So initially it was just sentences. Then people started to do kind of fixed length tokens or fixed length at character sets. Then they started to make it more semantic, where they were looking at semantically splitting up the text. And all of this had an impact, right? Obviously, because if you were to take just a text from a book and just cut it just at 50 characters, sometimes you're going to miss out what the rest of the sentence is going to say, right? And if you take it too long, now you're going to get a very big space in the middle, right? You have a lot of information that is not being put. So it is like a bit of a dance between trying to trade off the best way to chunk. And even now you have different types of chunking models. Like I said, you might use a fixed character, you might have fixed word length, you might look at sentences, you might look at just semantic meanings around. So you use the semantic meaning itself to chunk. And so these different types of ways, these chunks are getting actually created. So this is how the retrieval augmented generation pattern really works. So documents are broken up into chunks. They're using an embedding model. They are pushed into a vector database. And then what happens is that's at the ingestion stage. And so this is where you're actually preparing your vector database to be used within your organization, right? So very similar to how you would have done full text search, right? So in the days gone by, we had Elasticsearch, or we had Apache. Oh, it escaped me. So basically, you have Elasticsearch. So there was also a Lucene engine, the Lucene engine, full text search engines, right? So essentially, there, what you do is you take all this text and you push it to a full text search. So you can do a text search, right? A fast text search. So now what was happening was, rather than doing a fast text search, they're doing a semantic search, right? And so similar to when you made full text engines and full text indexes, here what you were doing is you were making what you call you're making vector database or semantic databases, right? So at the ingestion stage, all of this is pushed through into a vector database or a set of vector databases. And then what happens is, like, you come along and you have a query, and that query again goes to the same embedding model. And then based on that, it actually pulls up all the most relevant chunks which are within the vector database. They're all kind of then put together into a prompt template. So, like a prompt that you have, where you might kind of scaffold what you have with some additional information like rules. So you might say things like, make sure that it is factual, make sure that the information is from a verifiable source. You might do a set of rules there. Make sure the data is from any time after 2024. So all of those rules actually go into the prompt template along with kind of stylistic information. So you might ask, I need a JSON format back, or uh, I want a very concise answer, or I want a very long answer with evidentiary links in place. So all of that kind of gets pushed in here. And then again, that is pushed through to a large language model, right? So because now the large language model has all of this context it's able to work with, right? And then that actually sends the response back, right? So a word on context as well, right? Context also is interesting because context has changed over time. So a lot of these large language models also, and you would have seen this, initially they could only hold about 8,912 characters in them, or tokens. And so what that meant was RAG was very important because you couldn't keep all the information. Otherwise, what you can do is you can just push all of the words into the large language model and get the information, right? So what happened was that also changed over time. So what happened is over time that grew, and now I think Gemini in its Gemini Pro can actually handle 2 million context windows. So that's roughly, I think you can have about 3 or 4 books in that whole context window. But what happens there also is that most of the context window is taken up by the system prompt, right? So this is, I think, a very interesting truism. The fact that even with all of our advances, the most powerful way to really work with these large language models are the prompt, right? The prompt really makes a big difference in what you actually get out as an answer, right? So prompt engineering is still king, right? And you will see this in one of the in the assessment or the take-home assessment that you're doing. You know how different types of prompts will give you better outcomes than others. Great. So this is where the retrieval augmented generation acronym came from. So retrieval is where you're actually pulling in the most relevant uh, chunks. Augmentation is where you're actually pushing them into the prompt template along with your query. And generation is finally where the large language model actually takes that and generates your sequence of text, right? Which is generally your answer. So that's your retrieval augmented generation, right? So again, this changes over time, right? I mean, so this is the current space, but now people are saying agentic search is much better than what retrieval augmented generation does, right? So agentic search is where you actually split up your responsibilities within like a cohort of agents, which are then able to go and search very semantically across your text, right? Uh, so again, I think a lot of these kind of coexist from time to time, just because we are in such a rapid flux of change. I mean, but where we are now is scarcely believable from where we were last year, right? I think that's going to keep on going for the next few years. And so I think it's just a matter of picking up the most, what do you call it, foundational or the most, the technology which seems to make the most sense in terms of the way it's architected, and then you know that you have a bit of a leeway to be able to implement this and use that. Right, so RAG is still pretty much alive in the way that it's working, but agentic search is something that's being used a lot. Right, and so now we're just talking about vector databases, right? From here, we actually move into uh, graph databases or knowledge graphs, right? So with vector databases, what you're looking at is you're looking at information that's in data, this partitioned into chunks, and then kind of indexed as almost rows within the vector database, right? But when we talk about graph databases, they give a very interesting kind of concept where they're able to really look at the semantic meanings and really be able to arrange the concepts in a very organized manner, right? And this is where really knowledge graphs really come to the fore. Basically, you're able to take this information that you have and really model them in terms of nodes and edges and relationships between those edges. Now, the interesting thing about this is, you remember how we talked about vector databases? They can be one of the pieces that actually make up that knowledge graph as well, right? So now you have this concept of not just a retrieval augmented generation based on semantic search or based on vector-based semantic search. Now you have a hybrid search or hybrid architecture where you're able to look at semantically similar kind of concepts, which are modeled using the knowledge graph, and then within that, you're able to also do a vector-based search to be able to really fine-tune what that context should look like. And all of this is about getting that context right. So especially when you're working with a large language model, you want to be able to give it just the information it needs to be able to give you the correct answer. And also you want to be able to trace back and see that it has not hallucinated, it has evidentiary claims against it. And a knowledge graph really allows all of this, right? Because if you have a text chunk, you can now link it up to where the source is, the evidentiary piece of documentation or source or authority, and then that actually follows itself into the large language model as well, right? And so this is where essentially you're seeing this knowledge graph concept come in, right? So this is something that you probably would have tackled quite a few times or quite lengthily in the previous classes. So if you take your at the most base of this, you have the triples, right? The subject, predicate, and the object. And this kind of builds up the anatomy of that graph. And then if you take in how things are represented in terms of actual, say, like a production grade knowledge graph, it is like this, right? So basically you have these ontologies that are created to which actually preserve or model the relationship between these entities and also some of their attributes as well, right? So this is specifically around this thing of I think celebrity shoes, and in terms of the characteristics of those celebrity shoes, right? And then when you're able to pass these graphs, you are able to follow the most viable pieces of or the most viable traces to be able to get your answer, right? And then you're also able to infer things based on the connections between the nodes, right? And so this is what it would look like in terms of an enterprise knowledge graph, right? So if you look at it here, you have your document store, right? So this is where you have your actual documents. Maybe if you were to think back, Microsoft Fast Search, basically in SharePoint, you would have all of your different documents. And then from there, you would actually have your vector database, which actually has now a semantic embedding of all of these different types of text chunks, things that are most important, that are things that are most relevant and topical, and based on archival mechanisms. So like, the most used information is available at the closest tier, whereas the least used is kind of pushed back to the coldest tier. Right. And then on top of that, you have your text search engines. Remember, I talked about Elasticsearch or Apache Lucene uh, or uh, or similar. And then you have your data catalogs, right? You have your semantic data fabric. So this is basically where all of these knowledge graphs actually come in, where you're looking at users, entities, reference data, and you're looking at things like schemas, taxonomies, the domain knowledge, ontologies, and again, all of these things you would have been reading through and learning through in the past weeks. And then you have things like your large language models, you have your chatbots, you have your business intelligence, you have your downstream analytics. And then you have your your database, your gold standard database where your information is kind of kept in. And all of this kind of makes up your knowledge ecosystem within your organization, right? And generally, if you look at large organizations, they would have a very complex way of modeling all of this to be able to represent, right? Um, and you will see this in a lot of these new companies. For instance, Stripe does a lot of this work. And so what that has allowed them to do is that allows them to do things like fraud detection, that allows them at a very fast pace. It allows them to do things like site reliability engineering. Essentially, they are able to look at logs that are coming out of all of their cloud components and be able to find patterns where an error could occur, and they can what do you call put interventions in before the fact. They can diagnose after the fact, and all of this is now available through these conversational agents, right? And so it becomes quite powerful in the way that it works. So this is essentially how generally it will work. You have all of your data sources. You use a extract, transform, load paradigm. So essentially you're extracting the data, you're transforming it to a standardized format or the format that suits you. And then you're loading it into, you would have already learned about RDF. You're learning it to your graph DBs, right? And then you might use something like Sparkle to actually query those databases to give that information out, right? And that brings us to the last segment. I'll power through this as well. So this is where it actually all this starts to come into place or starts to make sense, right? It's not man versus machine, it's man and machine, right? So man is driven by goals. He uses an interface to be able to then communicate to the machine to be able to apply mechanical, electrical, or computational processes. Right. And this evolution of this computer interface has changed over time, right? You started off with your punch cards to console-based, like, your S400 kind of machines, to keyboards, to multi-touch, to the iPod, to the iPhone, to smartwatches. And now we have this new area of virtual reality, augmented reality, and chatbots, right? And so this is how that interfaces have also changed over time. But a lot of these, what you would find is a lot of them are reactive. Essentially, it happens when you actually go and do something, right? So how do we really change this into something proactive, right? So can machines kind of work on your behalf before the fact so that you don't have to really do that work, right? And this is where agents really come into play, right? An agent simply is a software that uses AI to accomplish a goal, right? And a more nuanced view of it is where you look at things like goal-oriented system, long-running processes, uh, metaphors, reductiveness, delegated authority. So you have from this very simple concept of a software that can run autonomously, to like all of these different paradigms of information, right? So this is an interesting one. This is an interesting conference. If you are interested in, you should actually look at. It's very practical. It's called the AI Engineer Conference that runs in the US. And you have a lot of these leading edge technologies coming in, and they talk about state of the art, right? So generally they are talking a lot in terms of the research. They're looking at, okay, how can we take the research and apply it to the next generation of problems we want to solve? So a lot of them are entrepreneurs. A lot of them are from that San Francisco Bay Area. So if you can try and have a look at some of these AI engineer podcasts, or you can actually have a look at the YouTube channels. They have some interesting talks with some of like, the forefront people in the forefront of technology, right? Especially from a software point of view. So that's a legal definition. An agent is someone who has the power to act on behalf of another person, right? And so that brings us to this kind of architecture. Essentially, here you have an agent. This is from a lady called Lillian Weng. She actually published in 2022 on a blog post, but it has been very pertinent in the way that it's captured this concept of agents, right? So an agent it has memory, short term and long term. It is able to plan, so it can do things like reflection, critical criticism. It can do chain of thoughts. It can do decomposition of goals, so it's able to plan how it needs to achieve a task. It has tools which it can use, and then it has actions, right, which it can invoke through those tools. And this is largely the agent infrastructure that most of these agents that are being used now actually follow. Right. And so there are some agent patterns. And a lot of these, what you're seeing in production, a lot of these examples are through autonomous coding agents, right? I mean, that's where they're actually looking at most of this information or seeing the practical examples of a lot of these agent design patterns. The other one is research. That's also something. And when I talk about research, I talk about it loosely, where it actually is able to go out and search the web on your behalf, or search a trove of documents on your behalf, or do some very defined experiments on your behalf, especially from a computational software point of view. Right. So here, this agentic design pattern. So this is from a gentleman called Andrew Ng. He is a Stanford professor, and he was the founder of Coursera, if you have used the platform. And he's quite a prominent voice in the AI space, especially the applied AI space. So you have an agent, a code agent, and you have a critic agent, and they kind of go between each of them. So each of them is it's essentially a software piece with a large language model component within it, with all of these different components. You can plan, it can memory, it can have actions and tools. And then it'll kind of go between itself to be able to look at bugs, fix bugs, and then test it itself. Right? So that is a reflection. You're kind of self-critical, or you're reflecting on what you have done. The tool use is essentially, if you take large language models, the biggest problem they have is they're trying to do all of that within this thing of auto regression, right? They're trying to achieve all of these very complex use cases using auto regression. But tool use became very interesting, where all the agent has to do is understand which tool it has to use. And the tool itself is very discrete. So it will always give the right answer rather than the large language model. So now you have the large language model, which is able to use all this fuzzy kind of logic or fuzzy kind of interpretations, and it's able to then plan and call tools which will achieve the goal, right? So for instance, if it's a research agent, it can actually now spin up a tool which can open a web page on your behalf and go through it and extract information. Right. So now that is all within a tool. So that is very computationally sound, or very deterministic in terms of the output. So now the agent is able to do what it's able to do better by using these different types of tools. Again, same thing with calculations, right? Or things like, let's say, for financial planning or monetization, or any of these different things that are very good or very well defined within software spaces, all can be a tool. Now, what you have is your agent is able to use fuzzy kind of methods of figuring out which of these agent tools need to be called in sequence, right? So this was around code execution. One is it can actually write its own code and execute it. And the other one is it can search the tool, the web for this. And you see this in a lot of the large language model platforms that you use now, right? So planning is essentially it's able to actually take a goal and then be able to break it down into sub goals, which it then can give to different tools, right? And the interesting thing here is you see this in a lot in these agents called Claude Code. That's an autonomous coding agent. Codex CLI. Those are all using this concept of planning, right? It plans out. Okay, you give it a spec of what you want to do. It plans out everything it needs to do, and then it goes out and does it, and while it's doing it, it reflects on exactly what it's doing, right? Eventually it gives you back the answer, and that is why a lot of these agents now, they take longer to deliver their answers, but they generally are able to capture the nuance much better, right? So there's one that I want to mention from Google, which is called Jules. They are looking at task windows of about 30 days. So essentially, they will give some task to the agent. It will go off for about 30 days, come back and give you the answer, right? So long running, long context windows, right? So here, now you can see how things are becoming more proactive than reactive, where you don't have to really be there and keep on clicking things. I don't know how many of you would have known when Windows Vista came around. It used to be horrible because every single action you do, there was a security risk that is thrown and you had to approve it, right? So this is the antithesis of that, right? Then we come to the next paradigm where you have multiple agents working in concert, right, to be able to give you a certain outcome. So this is a bit fantastic in the way it works. I mean, generally you won't be able to do this at the moment. I mean, the contexts are not long enough, but you get very smaller window tasks which are being done quite well, right? So one example of that is, again, like I said, the site reliability execution. So normally what would happen is when the site goes down, you have to call up your engineer in the middle of the night, whatever time it might be, and get them to fix it. Now, what the agent can do is it can actually look at all the logs. It can look at all the components that are available. It can do a root cause analysis and decide whether agent needs to be a software engineer needs to be called or not. If it can be done the next day, it'll keep in a holding pattern. So these small context kind of tasks, it's able to do quite well with these multiple agents, right? And so what are the agents like? So the agent might be, one will read the log file, one will be able to look at the past case, use case history, one will be able to contact the relevant parties. There might be a plan agent. So all of these actually live as autonomous agents within the system. So these are some of the kinds of agents you have. You have the coding agents like Codex CLI, Claude Code, Jules. Then you have these browsing agents as well. Comet is from Perplexity. And so these are essentially working on your behalf. Atlas is from ChatGPT. And then you have Manus, which is supposed to be a general purpose AI agent as well. Some of the AI companies to watch out for is Vercel is a very interesting company to look out for because they have a very good ecosystem they're actually building out, and they have a very good roadmap. They're working with Stripe, and they're looking at how they can build out sandboxed environments. Which can be sold, right? So it's very interesting how they're monetizing these models as well. I won't go too much into this, but watch out for Vercel. So they are the ones who actually made Next.js. This is an interesting one. This was from the Dharmesh Kwargesh. He had envisioned, if you go to agents.ai, you'll see this. He had envisioned that agents will come to a point where each agent will have a CV. Essentially, you can hire an agent from a platform and you can get it working on your task. And each of the agents will have their own CV of accomplishments. So think a LinkedIn for agents, and they have already kind of they're building out that future of what, or the future of what that could be. So it's interesting. I think this is the same person who co-founded HubSpot. So it'll be interesting to see where that actually goes. If you take some of these Codex CLI from ChatGPT or from OpenAI, the way they kind of talked about it is, okay, when you started working with your teams, initially it's going to be like an intern engineer learning new things. And as it gets more mature, it becomes better and better at coding, right? So it's almost like a physical digital agent or like a software training engineer, right? The engineer will get better over time. So similarly, you have these concepts of really almost like a digital species being integrated into workflows. So I won't go through this too. It's just like I remember I talked about site reliability engineering and using agents for this. This is just a graphic that actually talks about that. I'll share the slides so that you'll be able to look through. So I guess the next frontier for all of this is essentially all of this now going into the physical world, right? So that is robotics, and that is where NVIDIA is actually doing a lot of work in terms of humanoid robots and just standard robots and robotics, being able to really make those physical endpoints much more accessible. And this is where they say that, it will really take the next leap, because once you can autonomously navigate the physical environment, you're able to now capture a lot more data around, multiple modalities, right? Because at the moment it's virtual, right? Once you move into the physical, you can see a lot more data streams that are coming in, which then logically makes things easier to run. Great. So I think I'll stop with that. I already mentioned prompt engineering. This is something that to actually look out for. This is a very important part of, getting these large language models to work the way they should. Um, but I think most of you would have already seen this. For tomorrow, something that I would say is sign up for Neo4j. uh, this is one of the graph databases we'll be looking to work with in doing RAG-based implementation and multi-agent-based implementation. Just sign up for that. There's a free 14-day trial which you can use just to kind of try it out on your own, and we'll make sure that we have an instance for you running as well. And also have a look at the Cypher query language. They have some step-by-step manuals of how you can use Cypher. Essentially, it's a query language for graph databases, right? And so Neo4j actually uses this. And Neo4j is a production-ready enterprise-grade graph database. And generally, you find it being used a lot within company context as well. All right, great. That is a marathon talk.
Yeah.
Over to you,
Thank you.
Evgeny.
Thank you, Nishan. Thank you for this great lecture, putting the knowledge, engineering, and management in the perspective of Gen AI. So first, let's see if we have any questions from students. We have quite some of them being online. So it was lots of new information. So, but let's see. So, any questions? Hello?
Yeah, I have a question.
Yeah. Yeah.
This the thing about the LLMs, you mentioned that we've seen just a big spike in like the implementations of these. Is that due to the processing power being available, or do you think it would have come anyway? Uh, like
Um,
the because you handle so much data, so I mean there has to be some, because you can't just knowledge manage away the complexity.
No, you can't. And that is where these semantics really matter, right? That's why if you look at that enterprise knowledge graph, there were so many moving components. So you would actually tier it up. So you would have the most recent. So if you look at most storage mechanisms, you have the cold tiers and you have the hot tiers. The hot tiers are the most recent ones. The cold tiers are the furthest ones. And then you have, on top of that, you have this concept of caching. So again, on top of that, you don't do all that processing. You have some things which are pre-computed, which you can pull up on demand. So a lot of that comes down to software engineering in itself. In terms of these large language models, the only reason we got to where we are is because of the money they pulled into it. So OpenAI at that very initial part, they poured a lot of money into it, which really helped them, because I think some of these models, it takes something like $5 million to just do one training run. And this is without anything because let's say you start off a training run and say, oh, know what, I forgot something. You have to rerun the whole thing again, right? And they will run a lot of this. So to be able to kind of front up that money, and also to be have the hardware at the backing, that is actually what really helped these models come to being. And what the models did is they made the management part a bit easier, because now you have these models that can run uh, semi-intelligently, right, on all of this information. So I think it's a mix of two. The models one side, the architecture the other. And that is what really makes these work. And you see a lot of organizations really going down this path now. There are organizations that actually work specifically only on tuning models. So one thing was Meera Murati from OpenAI. She quit. She was a CTO, and then she started this place called Thinking Labs. And their first product, it was called Tinker. Essentially, it's like a SaaS platform where you can tune your own models. right? So what we're seeing here is like this infrastructure is becoming very easy for companies to use, and a lot of these organizations are now kind of breaking that mold and starting to use them. So again, like I said, models, architecture, those are the two things that I think are really driving this. I hope that answered your question.
Yeah, yeah, it answers the question quite
But
well.
it's
But then a
yeah,
follow-up question to that
yeah.
is, uh, you said the money is a big part of it. I mean, actually doing research on this that is not closed must be really hard to just get.
Mhm.
Like, what are these companies doing?
Mm.
How do you manage around that?
That's really
Yeah.
great question, Walter.
You want to answer that question? I think
No, no, go on. I mean,
okay.
I will complement
So,
with a couple of
okay.
comments. Mhm.
Right. So there are two things you can do, right? So if you can't beat them, you can join them. Then you get access to all of that money. But in the
Yeah, okay, go on, go on.
so the other part of that is, I mean, you need to really understand where to really focus, right? So one thing that we are finding is this, let's say even it's very hard to work in the large language model space. For instance, we
Mm.
don't have remotely enough funding to be
Resources.
able to match
And
them, right?
resources, actually, yeah.
And resources.
Computation.
And so something that we can really work on is one thing is look at new types of AI. You remember how I talked about one is a brute force and the other one is elegant approach. Maybe you can look at the elegant approach because that is the path that probably has the longest term effect beyond this short-term effect here. So that's one.
Mm.
And that doesn't require the resources. The second one is actually, if you look at this large language model, there are spaces in the application side of things. So for instance, creating the agents, creating the agent architectures, being able to kind of make interesting semantic ways of really bringing this knowledge together and implementing reasoning on top of it. So we don't work specifically on the large language models. We look at the application of it in very interesting ways. So everything from reinforcement learning to fine tuning, to those kind of things. Those things are kind of accessible within like research budgets generally.
Mm.
Um, yeah.
Yeah, I totally agree with what Nishan has said. So, in the academic world, so you try to identify fundamental problems. I mean, and there are plenty. I mean, yes, AI, Gen AI is super capable. I mean, it's mind blowing, really. I mean, every day I just amaze myself. It's like I'm like a child. But as Nishan said, it's a kind of I mean, it is achieved by this really brute force. It's not brute force search, but really brute force, like plenty of resources and at huge scale. I mean, we shouldn't forget that there are plenty of open fundamental challenges in AI. And one of the fundamental challenges is connected to how biological brains achieve same functionality. I mean, at physical scale of a single brain and just a fraction of power, taken for reasoning um, uh, and generalization and such. So, when you speak research and if you mean again academic research, so you should probably focus on fundamental challenges. And these fundamental challenges, they can be tried at simpler models. So you don't need to experiment with GPT-5 above, whatever. So the models that Nishan mentioned, and I mean, you can easily make hooks to GPT-2 and test some ideas there. So this is the way to go. But then, and again, so if your interest is more in applied research, then there is, I mean, plenty of space there as well. So I mean, but then you probably need to resort on kind of agentic level, so that uses these models. Did we answer your question, Walter?
Yeah, yeah, I think there's a clear answer,
And
especially
yeah,
the
sorry.
part where that you have to choose something else that doesn't require the amount of funding because the training itself is
Absolutely.
the reported
And
costs.
as a side note, we have plenty of research ideas. I mean, in our collaboration, LTU Square, really on the intersection of these fundamental challenges and applied AI. So, I mean, if you are interested, we are always open to talk and discuss possibilities. Right. So let's check for more questions. Maybe are there any more questions? Okay. Listen, once again, Nishan, thanks for the first introduction. So actually, it was really great excursion to LLM. And I mean, I find this topic is really amazing because I mean, we are now we are located on I mean, on this part of spiral that kind of incorporates all the previous incarnations, like all these multi-agent architectures that were famous back in the end of 90s, beginning of 2000, plus knowledge management. So now it all
Yeah.
come back within LLMs. And so we try to form this home assignment for you that, just to try it out. I mean how this interplay between LLMs and knowledge representation can work. So tomorrow you will see continuation. So agentic AI knowledge databases. So that's kind of extra material to look ahead. So to make you interested. And again, so collect your questions for home assignment that was published. And just bear in mind you have almost 1 month for you. Well, with some holidays in between, but it will be fun. By the way, if you have any questions about home assignment, I'm still here for maybe next couple of minutes, if or whatever it requires. And Nishan, thanks for now.
Thanks, everyone. Thank you for a good audience.
Okay, see you tomorrow, same time.
Yeah.
So, any questions regarding home assignment on or anything else in the course?
Not on the home assignment, but just to make sure the lab 3 is this Friday on
Yeah,
12. Yeah. Okay.
yeah.
Yeah.
How is it going? I mean, just give me an indication.
Part one was
Easy.
yeah, it was kind of straightforward.
Yeah,
Now the part two,
yeah.
all
So
just have to. I have some numerical errors where I get values above 1 and I can't
yeah.
find out where, but
Okay.
I haven't I haven't spent too much time looking on it, but I know it's wrong at least.
Yeah,
So
yeah. But again, I mean, just to give you, I mean, Nishan has mentioned, so that's, I mean, the idea was to give you a little bit of touch on this academic research formulation. So I hope you find it interesting. Any
but
more issues or comments? So let me check. No, nothing in chat. But then listen, so great that you joined. So tomorrow, 8 a.m., same place. See you. Bye bye.